so let's get started. I would like to talk, as Ivan said, about conflict-free replicated data types, or CRDTs. I will start with a brief introduction about what they are and why we might want CRDTs, but most of the talk today will be new material. So this is research that we've only just done within the last year or two, solving some of the open problems that there were with CRDTs. So yes, as Ivan said, you might know me from this book, Designing Data-Intensive Applications, which has also been translated into Russian amongst several other languages. So if you're interested, you can find that. But today I'll be focusing on collaboration software. And I understand collaboration software quite broadly. That is any kind of software where several users can be contributing or editing or updating some shared either document or file or database or other state. And so there are lots of examples of this kind of software. Of course, Google Docs comes to mind as like a type of collaboration software where several people can update a shared text document. Of course, Office 365 is the equivalent of that, but there are also tools like Figma, which does a similar thing for graphics software, but even software like Trello, where several users can manage tasks and assign tasks to each other and leave comments and so on. All of these software have in common that several users can concurrently update the data. So I'm going to take text editing as an example, and a lot of the talk will be about text editing, but always keep in mind that this applies to really quite a broad range of different types of software. And so what you might happen in a collaborative text editor is that two users concurrently update the document. So two users make changes at about the same time without knowing about each other's change, and only find out about each other's changes later. So let's say we have two users here, red and blue, and they start off with the same document, which is hello exclamation mark. And then the red user edits this document by inserting the word world before the exclamation mark, while concurrently the blue user edits the document by inserting a smiley after the exclamation mark. And then as those two users subsequently communicate over the network, say over the internet, what we want is for them to both end up in the same state. So we want their documents to converge to the same document, and for that document to reflect all of the edits that have been made. And so the final document in this case is reasonably obvious. We want both the insertion of world and the insertion of the smiley face to be preserved. So the merged result is hello world exclamation mark smiley. So there are a bunch of algorithms that have been developed for allowing this sort of concurrent editing. What you do get this sort of concurrency even just when the two users are online and they're typing at the same time. But you can imagine a lot more sort of divergence may happen if the users are allowed to edit the document while they are offline. And so they might work on the document for hours, and then only hours later, then when they get an internet connection again, merge their results together. And so in this case, you have a sort of branching and merging workflow, much like what you might get with a version control system, such as Git or so. And in those systems, in these collaborative software, though, we generally want to not have to manage the merge conflict by hand, but we want automatic merging of any changes that were made concurrently. And there are at a high level, there are two families of algorithms that have been developed to allow several people to concurrently update a document. Google Docs and many existing applications are built on a family of algorithms called operational transformation, or OT. And there is also a more recent, newer family of algorithms called CRDTs, which has only come up in the last 15 years or so. They solve broadly the same problem, but they solve it in quite different ways. So let me start briefly with a summary of how operational transformation works, so that we have a bit of context. So for this example, let's say we've got, again, two users. They both start off with a document that consists of the letters H, E, L, and O. And the two users now concurrently update this document. So the green user on the left inserts a second letter L, while concurrently the purple user on the right inserts an exclamation mark after the O. And we want to merge these changes together. So the way this is done in operational transformation is that whenever we record a change to the document, we record this as an operation, and the operation describes either inserting or deleting a character at some position in the document, which means we have to have some way of describing at which position we are making a certain edit. And the way this is done with operational transformation is that we use the index of the character into the document, or the position which just counts first character is 0, second character is 1, and so on. And so if we want to insert the L so that we have a second L on the left-hand side, this is inserting a letter L at position 3, as you can say, at index 3 in this document. And on the right-hand side, the exclamation mark gets inserted at position 4, or index 4. Now, as these two users communicate and exchange their edits, these operations get sent over the network via a server to the other user. And so the user on the right now receives the insertion of the letter L from the left-hand user. And so this user just inserts L at position 3, and we get the result that we wanted, which is hello with 2 L's and an exclamation mark. Now, in the opposite direction, taking the insertion of the exclamation mark from the right-hand user and applying it to the left, notice that something subtle has to happen here. So if we simply take the operation as it is, insert exclamation mark at position 4, and we apply that to the document on the left-hand side, inserting the exclamation mark at position 4, what we would get is hell exclamation mark O. So the exclamation mark would be put before the O, not after the O, because what has happened on the left-hand side is we concurrently inserted the L at position 3, and so now all of the indexes after 3 have moved along by 1. And so what has to happen here is that this position, number 4, needs to be transformed into position 5 so that the exclamation mark appears after the O, as we want it. And so this transformation of indexes from 4 to 5, this is why the algorithm is called operational transformation. And this is also the main difficulty with this algorithm. So the big assumption that most realistic operational transformation algorithms make is that all of the communication has to go via a central server. So that is, if you've got 2 users who are collaborating, even if those 2 users are in the same room, and even if they could actually just exchange their edits over Bluetooth in the same room, they nevertheless have to go through a single central server that is provided, for example, in Google Docs by Google, because the OT algorithm assumes, for its correctness, it assumes that all of the edits are sequenced by a singleton server, which means now that any sort of other channels of communication are simply not allowed, even if those network communication channels exist, be it Bluetooth or be it a peer-to-peer network, for example, or be it even passing USB sticks between people, whatever it be, those communication channels cannot be used because it would undermine the assumptions of the OT algorithm. Everything has to go through the central server. And so this is where CRDTs come in. CRDTs allow a similar kind of conflict resolution, but they don't make any assumptions about the network topology. They don't make any requirements that all of the communication has to go through a single server, which makes them potentially more robust and applicable to a wider range of systems. So we can use CRDTs to build new types of applications that are not really realistic with operational transformation. And so the main correctness property that CRDTs and OT provide is convergence. And convergence means that if any 2 users have seen the same set of operations, then their documents must be in the same state. And this is the case even if they actually received these operations in a different order. So no matter in which order the operations arrive at the different users, we want that the final document that users see on their screen to be the same. This is like a basic minimum requirement of consistency. If we didn't have this, it would mean that users are permanently inconsistent with each other, which is not great. So this is like the basic level of correctness for CRDTs. But actually, it turns out that convergence by itself is not really enough, because all it says is that all of the users converge to the same state, but it doesn't really say what that state is. And what we will be looking at in this talk is several examples where actually, we can reach a state that is the same for all of the users, but if that state is not a state that we actually wanted, then the algorithm is still not fulfilling its purpose. And we need to, in addition to convergence, we also have to develop some ways of making sure that the state that the merged result that we receive at the end is indeed the result that we wanted. This can be a bit difficult to define sometimes because it relies on some kind of intuitive human notion of what is a desirable outcome and what is not, but we will see some examples in this talk. So I have come to the conclusion after several years of working on CRDTs that basic CRDT algorithms are really simple to implement and quite nice, but unfortunately there are a lot of CRDTs that are easy to implement very badly. And really what we will be looking at now is several ways of trying to overcome that badness and implement CRDTs that are better than what is already known. So there are 4 particular examples that I want to look at over the course of this talk, and I will go into each of them in some detail. And I'm going to start with one that I call interleaving anomalies. And so this is a problem that can occur in collaborative text editors, where you've got several users concurrently inserting text at the same place in the document. So this problem I will illustrate by first looking at an example of how a couple of CRDT algorithms for text editing actually work. So I said for operational transformation, the basic way that we address a particular position in the document is by using the index of the character, counting from the beginning of the document. And CRDTs avoid the need for this operational transformation by not using indexes as the way of saying where we insert or delete a character. But instead, what they do is they give each character in the document some kind of unique identifier. And different algorithms use different constructions for this unique identifier. But one popular way of doing this, at least conceptually, is that we use fractional numbers. So say we have rational numbers and say we want the document to be represented by numbers between 0 and 1, where 0 is the beginning of the document and 1 is the end of the document, and we can just pick any numbers between 0 and 1 to represent positions of characters within the document. And so in this example here, I've got, again, a document consisting of H, E, L, O, and I've given H a position of 0.2, E a position of 0.4, L a position of 0.6, and O a position of 0.8. And so what we can do here is now, if we want to insert a second letter L between the existing L and the O, we can pick a number between 0.6 and 0.8, say we pick 0.7, and make that the position of this new character. And if we want to insert the exclamation mark after the O, we pick a number between 0.8 and 1, so for example 0.9. And so now the state of this data structure can be represented as a set of tuples. So we start off with a set of tuples where we have each character H, E, L, and O tagged with the number that identifies its position, and maybe also tagged with what I've called here A. This is the ID of the node or the user who inserted that particular character. And the reason we might want to include that ID of the user who inserted it is because if you have two users concurrently inserting at the same position, they may generate the same number, and then the ordering of those characters would no longer be well defined. So we can use the ID of the user who inserted a particular character as a tie break in case 2 users generate the same number. And now we can add to this set here the 2 new elements for 0.7 and 0.9, the L and the exclamation mark. And we can just take the set union and we get this new set of tuples, and reconstructing the current document from these tuples is simple. We just order them by their numbers and then put the characters in that order. And so this seems like a reasonable construction, but unfortunately it has quite a significant problem. And that problem is illustrated in this diagram here. So here we have 2 users, 1 on the left, 2 on the right. User 1 and user 2 both start off with a document that says hello, exclamation mark. On the left, user 1 inserts the word Alice after hello, before the exclamation mark, so it says hello Alice. And on the right, user 2 inserts the word Charlie before the exclamation mark, and so it says hello Charlie. And these two insertions happen concurrently, and now the users communicate, they exchange their edits, and what we get out at the end is some kind of weird mess of letters. I don't even know how to pronounce this. It's just a weird mixture of characters. What has happened here? Well, what has happened here is illustrated in this diagram. We start off with hello. Each letter has a number as before, where O has 0.64 and the exclamation mark has 0.95. And now the red user on the left allocates new numbers to each of the letters that is being inserted. So within that range, between 0.64 and 0.95, the space and then Alice are given numbers within that range. And concurrently and independently, the blue user on the right also picks numbers for each of the characters between O and exclamation mark, so all of the characters, space and then Charlie. They also get assigned numbers between 0.64 and 0.95. And the exact choices of the numbers here, well, is not really relevant, and various algorithms often randomize the choice a little bit because that avoids too many users colliding and picking the same numbers. But unfortunately, this also has the consequence that now if we take all of those characters that were inserted in this number range between 0.64 and 0.95, well, we get an interleaving of the insertions made by the left-hand user and the right-hand user. And the result is just this jumble of characters that is totally unreadable. So note here, in this case, we've only inserted a single word, and we've nevertheless ended up in a result that is unreadable. Things get even worse if the users are inserting a whole paragraph or maybe a whole section at the same position. And this is a very realistic thing that could happen in practice. Imagine that two users are editing a document and they're each inserting a paragraph at the beginning of a certain section or at the end of the document. So they would be inserting a whole paragraph at the same position. And the end result from these concurrent insertions is potentially that all of the letters in the paragraph are jumbled up. The result will be completely unreadable. It will just have to be deleted and thrown away and rewritten again from scratch. And the users will not be very happy with this. And so we have looked at a bunch of different existing CRDT algorithms for text and examined whether they have this interleaving problem. And we found this interleaving problem in at least two algorithms, that is Logut and LSEQ. And unfortunately, the way these algorithms are designed, this problem is not really easy to fix either. The problem is really inherent at the foundations of how these algorithms are designed. And we have not been able to figure out a way of fixing those algorithms so that this problem does not occur without changing the entire algorithm. Now, some existing CRDT algorithms, we have not found this problem, such as TreeDoc and Woot. However, unfortunately, these CRDTs are also the ones that are the least efficient. So they have the biggest overheads. The whole reason why LSEQ was designed, for example, was in order to improve the performance relative to TreeDoc and Woot. So we can avoid the interleaving anomaly by using these very inefficient algorithms, but that's not really a great solution either. A strong here is not actually a CRDT algorithm, but a specification of how collaborative text editing algorithms should behave. And this formal specification also allows the interleaving anomaly, unfortunately. Now, finally, RGA is an interesting one. So the RGA algorithm does not exactly have this interleaving problem that I explained just now, but it has a lesser one, a less bad one, and I'm going to talk about that briefly now. So in RGA, what can happen is the following anomaly. So here on the left-hand side, we've got, again, user one. User one first types the word reader in between hello and the exclamation mark, and then inserts the word dear, so that the final result is hello, dear reader. So what has happened here is the user positioned their cursor before the exclamation mark, typed space reader, then they move their cursor back just immediately after the hello, and then typed dear. So this moving the cursor back is a crucial part of this operation here. On the right-hand side, the user just types the word Alice between hello exclamation mark. And what can happen now is that the word Alice gets interleaved between the word dear and the word reader. So one possible outcome with RGA is the text, hello dear Alice reader, which is not as bad as mixing up the characters individually, one by one. Instead, we have these sequences of characters which can get interleaved. And the reason why this can happen is that RGA uses a structure that looks a bit like this. So RGA uses these very deep trees where the parent of each character is the predecessor of that particular character at the time the character was inserted. And so you can think of this as where you position the cursor and then where you start typing. And so you start off with hello exclamation mark, and then there are 3 occurrences of the cursor being moved after the O, and the user then typing space reader or space Alice or space dear. And there, RGA in this case allows 3 possible outcomes. It allows hello dear reader Alice, or hello dear Alice reader, or hello Alice dear reader. And I would not like to allow the second one of these, because in this case Alice has been interleaved inside the insertions of dear and reader. But the other 2 outcomes are reasonable, acceptable outcomes. So in this case, which of those 2, 1 and 3 is chosen does not matter too much, really. So with RGA, the worst case really you can get is if the user types the entire document character by character from the end to the beginning, so in reverse order. If the entire document is typed in reverse order, then you could get arbitrary character-wise interleaving, because at this point, every single character is essentially moving the cursor back to the beginning of the document. So on the assumption that most people do not type documents back to front, most people tend to type documents in a reasonably linear fashion and occasionally only moving their cursor position, then the interleaving problem in RGA is much less bad. So for this reason, we have been preferring RGA in our work over some of the other algorithms, because I think the interleaving problems in for example, logut and LSEQ is really unfixable and is pretty much rules out the use of those algorithms, unfortunately. So we did, in fact, develop an algorithm for RGA that fixes even this lesser interleaving property, but I don't have time to talk about it in this particular talk. If you want to see it, it's in a paper. So we had a paper on interleaving anomalies at the PAPOC workshop in 2019, and it describes the algorithm in great detail, showing how to prevent even this interleaving anomaly here with RGA. So I'm going to move on in this list of 4 things that we wanted to discuss today. The next thing I want to talk about is moving items in lists, that is, reordering list items so that we want to move an existing item to a different position. This is work that we published only a couple of months ago at the PAPOC workshop this year. And so let me start again with an example. So let's say we have a to-do list, and one common thing that people want to do on a to-do list is to drag and drop the items on the to-do list to reorder them. So to put the items in a different order, in order of priority or whatever you want. So let's say we start off with a to-do list consisting of firstly buy milk, secondly water the plants, thirdly phone Joe, and say the user wants to drag and drop phone Joe and move it to the top of the list, so that now phone Joe is on the top and buy milk and water plants have moved down by 1. So now we can represent this kind of data structure, a to-do list, using a list CRDT, which is essentially the same as all of the existing text editing CRDTs, like the ones we talked about in the last section. And here, with all of these existing CRDTs, we do not actually have a built-in move operation. So the CRDT does not actually define how we can move an item from one position in a list to a different position. All these CRDTs offer is deleting an item and inserting items at any position. So now we could say, okay, well, it's easy enough to emulate a move operation by deleting the item from its old position and reinserting it at its new position. So let's have a look what happens if 2 users concurrently do that. So here I've got replica A, the user moves phone Joe to the beginning of the list, And concurrently on replica B, the user also moves the same item to the same position, also at the top of the list. What happens when these two replicas now communicate? Well, if we have implemented the move operation by deleting the item from its old location and reinserting at the new location, deleting from the old location twice is the same as deleting it once, but inserting at the new location twice, that means it's inserted twice, which means we end up duplicating this item. So we end up with two copies of the to-do item phone Joe, which is not really a great outcome. This is not really what we wanted. This is unfortunate. So, well, what can we do about this? Or let's think about, firstly, what do we actually want to have happen in this case? Let's think of a slightly different example where the two replicas still move the same item in the to-do list, but they move it to two different positions. So replica A moves phone Joe to the top of the list, while replica B moves phone Joe to be after buy milk, to be at position 2. So what is the expected outcome? One option would be to duplicate so that phone Joe appears in both position 1 and position 2, but as I said just now, I think that is undesirable. So that means the only other reasonable possibility is that the item appears in one of the two destination locations. So either finally in the final stage, phone Joe appears at position 1, or it appears at position 2, but not both. And so we can say that, let's say here, we're going to pick one of the two, if they're conflicting different positions for the same item, we're going to pick one of the two arbitrarily but deterministically as the winner. And so in this example here, I've said, okay, phone Joe being at position 1 is the winner, which means then that all replicas converge towards having phone Joe at the top of the list. How do we implement this? Well, if you know the existing work on CRDTs, this might smell kind of familiar. What we're doing here is we are looking at several concurrently assigned values, several concurrently written values, and of these different positions of the item, we're picking one arbitrarily but deterministically. This is exactly what happens in a last writer wins register. So in a last writer wins register, you've got several users who can update the value of the register. The register is just like a variable that can be overwritten with a new value. And what happens is as they synchronize, one of the values that was written concurrently gets picked as the winner, and this might be picked based on timestamp, for example, or some other kind of arbitrary criterion, and everybody converges to the same value, and the other values get thrown away. And this is exactly what we want in our case of the list move here. So you can think of the position of each item in the list being a last writer wins register, and the value contained in that register is a description of the position of that particular item. And so here, when replica A sets the position of phone Joe to be head of the list, and replica B sets the position of phone Joe to be after buy milk, as these two converge, we want both to converge on the same value for the register that describes the position of phone Joe. And the final value could be, for example, then head of the list. So this now means we can actually use an existing CRDT, which is the last writer wins register, to construct this move operation. We need two things actually here. Besides that register, we also need a way of describing the position of a particular item in the list, so that that is the value that will be contained in this register. But well, if you think about it, we already have this, because as I said earlier, all of the CRDTs for describing lists or text editing work by assigning a unique identifier to each element in the list, or to each character in the document. What exactly this identifier is depends on the particular CRDT algorithm. So in TreeDoc, the identifier is a path through a binary tree. In Logoot, it's a path through a more complex tree with a higher branching factor. In RGA, it's a kind of timestamp, and so on. And so all of these CRDTs already have a stable way of referencing a particular position in the list. So we can just use that existing list CRDT in order to generate our positions for places in the list, and then when we want to move to a new location, we just allocate a new position identifier at the location where we want to move the item to, take that position identifier and put that position identifier in our last writer wins register. Secondly, now, we need a separate last writer wins register for each item in the list. But that is also easy because we can use, for example, an existing set CRDT type. So take, for example, an add-wins set. We can now construct this add-wins set where each element of the set is one item in our list, in the to-do list, for example. And each item consists of a pair. It's a pair consisting of the value of that item, which could be like the description of the item on the to-do list. And secondly, now, the last writer wins register containing the position of that item. And so here we can put the last writer wins register inside the add wins set, and we can put the identifiers, position identifiers from the list CRDT in the last writer wins register. And now by composing these three CRDTs, we've constructed a new CRDT, namely a list CRDT that has a move operation that allows us to atomically move an item from one location in the list to another. Very nice, I think. And so the nice thing is also this will work with any existing list CRDT, and we can upgrade that list CRDT by using this technique here to support a move operation. Now, so far we have only talked about moving individual items in lists. And this makes sense in a to-do list where the drag and drop, you can typically just drag a single item at a time. If you want to move several items, then you move them in separate operations. And so moving one item at a time is fine. But in text editing, you might imagine a more general type of move where actually you want to move a whole sequence of characters in one go. And so let's take here we have our to-do list represented as a text document. So just as a linear sequence of characters where each item on the to-do list starts with a bullet point character and ends with a new line character. And in this scenario here, replica B wants to take the item milk and move it ahead of bacon in the list. So it wants to take the whole sequence of characters consisting of bullet point space MILK new line and move that entire sequence to be ahead of bacon. Concurrently, another replica, A here, might change milk to soy milk, and it does this by deleting the uppercase m and inserting soy and lowercase m. And so here we end up with two different documents produced by these two replicas concurrently, and now we want them to communicate and converge converge to the same state. And intuitively, what we expect to have happen in this scenario here is that, well, the milk is moved in front of bacon, and milk is also changed to soy milk. So the end result is that we have firstly soy milk and secondly bacon. Unfortunately, if what we do is take the CRDT, the move operation CRDT construction that I just described, so the construction for moving a single list item, if we take that construction and use it to move these entire sequences of characters, we get this outcome here, which makes me sad. In this outcome here, the sequence milk is correctly moved in front of bacon, but the edit that changes milk to soy milk, that remains attached to the old position of the word milk. So the end result is now we have bullet point milk, bullet point bacon, and then soy M, just letter M, stranded there without its context, because unfortunately the insertion position of the letters soy M still remain after bacon, so the insertion position has not been moved to the new location. It is probably possible to fix this, but so far we have not yet managed to fix this, and a couple of people are thinking about how we might be able to do these moves of ranges of characters in a way that is safe, but it is quite a tricky problem. So if you want to think, you can think about that and see if you come up with any solutions. I'm now going to move on to the third of our list of 4 examples that we want to talk about here. So the third is also about moving, but this time, rather than talking about lists, I'm going to talk about tree data structures. So trees are very useful because, for example, the file system on your computer is a tree consisting of directories and files, or a JSON document is a tree, or an XML document. All of these things are trees. And if your application manages a tree, maybe because it's a distributed file system, or maybe because it's a JSON document in which you can move entire subtrees of the document around, then, well, you also want a move operation. And so with a move operation on trees, we have firstly a problem that is exactly analogous to what we just talked about in the context of lists. That is, what happens if several users concurrently move the same node in the tree to a different location? So in this example here, we've got replica 1, which moves the node A to be a child of B. So here A, and including all of its children, A1, A2, A3, gets moved to be underneath B, while concurrently on replica B, that same node A is moved, but it's moved to be a child of C instead. What do we want the outcome to be here? So I've listed on the right-hand side 4 possible outcomes, A, B, C, D, for what could be merged end results. So one option is we duplicate, like we had in the case of moving items in lists. Duplication is kind of the easiest way, but also not a very great way of dealing with this. In the case of duplication, we would have A appear as a child of B and A appear as a child of C, but we would have to now also copy all of the children underneath A, so that entire subtree would end up being cloned. So we have copies of A1, A2, A3 twice now. This is not particularly great. In most applications, you don't actually want this. Well, another option would be to have for A to be a child of both B and C, but now our data structure is no longer a tree, it's now a DAG, or some kind of more general form of graph. So I think the only sensible options in this case here are the options marked C and D, where we have A either as a child of B or A as a child of C. In other words, we choose one of these two outcomes as the winner, and we throw away the old one. And exactly like we had in the case of list moves, that seems to be the most reasonable behavior if 2 users concurrently move the same item, the same node in the tree. But with trees, we have an additional complication. And this complication can be illustrated on a file system. So you could try this on your computer if you like. It's kind of an amusing little thing to try. That is, you create a directory called A, then you create a subdirectory called B within A, and then you try moving A into B. That is, you try to move A to be a subdirectory of itself. What happens in this case? What we're trying to do is kind of move a directory inside itself, which doesn't that kind of create a loop or something like that? I tried this on macOS. The error message I got was renaming A to A/B/A, invalid argument. And I imagine most operating systems whose file system is a tree will behave in a similar way, because if we allowed this move to happen, we would end up with a cycle, and our file system would no longer be a tree. So what happens here in the case of CRDTs is unfortunately a step more complicated, because it's easy enough to detect this particular example of a user trying to move a directory into itself. So we can fairly easily detect that the user is trying to do that and stop them from doing that. But in the case of CRDTs, look at this problem here. So on replica 1, the user takes the node B and moves B to be a child of A. So now A is a parent of B. On the other hand, in replica 2, the user takes the node A and makes it a child of B. So replica 1 moves B into A, replica 2 moves A into B. Each of these operations by itself is perfectly fine and safe. But what happens when both of them are combined? Well, we end up exactly with the problem that we just had, where we try to move a node underneath itself. And so, as before, if we are not careful, we can end up with the outcome shown here in the box marked A, where A and B have ended up looped up in a cycle, disconnected from the tree, and our data structure is now no longer a tree because we've introduced a cycle. Another way of solving this is, again, duplication. So we could say that we have both A being a child of B and B being a child of A. And in that case, we would have to clone A and B and its children, as shown in the box B on the top right here. This is a possibility, but it's not particularly great either, because, again, we've got duplication. So as before, I assert that the best outcome here in this case is, again, that we pick one of the two states as the winner and throw away the other move operation. So in that case, either we have B as a child of A, or we have A as a child of B, but not both of them. So you might wonder what real software actually does in this case. So I tested this with Google Drive, for example. So tested exactly this example where on one computer I moved A inside B, on a different computer I moved B inside A, then let the two computers sync their states, and Google Drive just gave me this error message here. An unknown error occurred. So even Google can't get this right. But for CRDTs, we do want to get this right. And so I'm now going to describe an algorithm that we developed for allowing these kind of move operations on trees in a way that is safe and that prevents us from having any errors like this and prevents us from introducing cycles. The way we're going to do this is we think about the sequence of operations that have been made on each replica. So on replica 1, let's say we have here operations 1, 3, a move operation, and 5, and we give each operation a timestamp. So operation 1 has timestamp 1, operation 3 has timestamp 3, and so on. And so here on replica 1, we have the move of A into B, and in replica 2, we have the move of B into A at timestamp 6. And so, as I said before, each of these move operations by itself is safe, no problem at all. The problem arises only when we combine both of them together. And so what we can do is to take the operations that were generated on each of the replicas and to put them into a single list in which we have sorted all of the operations by their timestamp in ascending order. And in this case now, if we go through the operations in increasing timestamp order, you can see that the first move operation of these two is safe. But when we come to the second move operation, at this point now, move B into A, at this point we have to detect that performing this operation is no longer safe, because actually now A is a child of B, so moving B into A would be introducing a cycle. And so in that case, we have to figure out that we have to skip that operation. Now, the problem is here, if you think about this from the perspective of replica 1, the replica 1 has already applied the operations with timestamps 1, 3, 4, and 5. What now happens when replica 2's operation needs to be applied to replica 1? What we really need to do is to insert the op2 that came from replica 2. We have to insert that into the right position into this sequence of operations that has been already executed by replica 1. So at this point, it's too late to just append the new operation with timestamp 2 at the end of the sequence of operations, because now they would no longer be in the right order. And for our detecting which operation is safe and which operation is unsafe, it's important that we know exactly the order in which we apply the operations, because that determines exactly which one is safe and not. And so we devised a quite simple but reasonably elegant algorithm for inserting this new operation with timestamp 2 here into the sequence of operation that replica 1 has already performed. And the way we do that is by allowing operations to be undone. And so in particular, now if replica 1 wants to apply this new operation with timestamp 2, and it's already got timestamps up to 5 in its log, it's now going to process this log in reverse order and undo timestamps, undo all of the operations whose timestamp is greater than the operation that's just come in. So in this case, we have to undo op5 with timestamp 2. We have to undo the move operation with timestamp 4. We have to undo the op3 with timestamp 3. Now we can apply the new operation with timestamp 2, and then we can redo the 3 operations that we just undone. And the end result now is that we have this log of operations that were applied effectively in timestamp order, provided that we can always do this undo in a way that exactly reverts the effect of that particular change. Now, you might be wondering, isn't that really expensive to have to constantly do these undos and redos in order to put the list into the right order? And yes, there's certainly a certain amount of cost to that, but we did some experiments in which we had 3 replicas which we deployed across 3 different continents, so there's a significant network round-trip time between those replicas, and then we just got them all to generate lots of move operations, and the faster they generate move operations, the more undoing and redoing needs to happen. And we noted here that the time that it takes to apply each individual operation grows roughly linearly with the rate at which we're applying operations, because the number of undos and redos that you have to do grows roughly linearly with the number of operations. But nevertheless, with a fairly simple program, we were still able to process about 600 operations per second, which is, it's not a huge amount in some kind of big data system. But if you're thinking of an application where it's a single user performing edits to, say, their local file system, well, 600 operations per second is way more than what a single user is going to perform on their individual tree. So for many applications, actually, the performance is just fine. It's perfectly sufficient. Let me explain briefly the data structures that underlie this particular algorithm. So in order to describe a move operation, we use a data structure that looks something like this. So each operation firstly has a timestamp. The requirement is that the timestamp is globally unique. This can easily be achieved by using Lamport timestamps, for example. And now we have some way of referring to the IDs of nodes in the tree. And so here, child is the ID of the node that we are moving, and parent is the destination of where we want to move the child to. So it's the new location of child in the tree. And meta is here some metadata that we can associate with this parent-child relationship. So imagine if it's a file system, then meta might be the file name that a particular inode has within, a file inode has within the directory inode, which is its parent. So metadata here would be the file name in this case. So note that in this operation here, we do not note what the old location of the child is. So what this operation does is it simply takes the child from wherever it currently happens to be in the tree, steals the child from its own old location, and moves it to the new location. And when we now construct this log of operations, we need to add a little bit of extra data, which allows us to perform the undo and redo. And so for undo, whenever we perform a move of some child, we also need to record its old location and its old metadata. And then undoing a move operation is simply putting the child back in its old parent and its old metadata, and redoing it is just a matter of moving it again. And so now we can describe the move algorithm like this. So firstly, we define what it means for A to be an ancestor of B. So firstly, A is an ancestor of B if A, M, B is in the tree. That is, A is a direct parent of B in the tree. Or A is an ancestor of B if there exists some other tree node C, such that A is a parent of C and C is an ancestor of B. And given this definition, we can now define our move operation like this. So here, we perform our move operation. We first look, is the child, that is the node that we are moving, already an ancestor of the parent? So is the child that we are moving an ancestor of the destination of our move operation? If so, we would introduce a cycle by executing this. So we drop that operation. Likewise, if the child and the parent are in fact equal, then also we would introduce a cycle. So we drop the operation. Otherwise, it's safe to perform this operation, in which case we remove the old parent-child relationship from the tree and we insert the new parent-child relationship from the tree with the metadata. And so for this algorithm, we proved its correctness. So we proved that for every tree that goes into this, this operation here, any operation that you apply will preserve the tree property. So the data structure is a tree firstly, if every node has a unique parent, and secondly, if the tree contains no cycles. And so we proved that the move operation preserves these two properties. And finally, of course, we want to prove that this is in fact a CRDT. So no matter in which order you apply the operations, if you have two users who apply the same set of operations, they end up in the same state. So in other words, the operations are commutative, and we proved this as well. So that's enough for moving subtrees around. I want to finally get to the last part of this talk, which is on improving the performance and the efficiency of CRDTs. So this has been a major problem with CRDTs pretty much since they were invented, which is the metadata overhead, that is the amount of additional storage and network bandwidth that we have to use just in order to enable the CRDT properties. So if you think about the CRDT, the text editing CRDT that we talked about earlier, we give a unique identifier to every single character in the text document. And so here, for every character in the text document, if it's English text, this will be just 1 byte for the UTF-8 encoding for that character. If it's Russian text, for example, it will probably be 2 bytes per character. But it's a small amount of data for each character in the document. But then on top of that, well, we need this position identifier, which is in reality some kind of path through a tree. So the size of that depends on the length of the path, but it can easily be a couple of dozen bytes, if not 100 bytes. Then we probably will also want some kind of node ID, that is the identifier of the user who inserted this particular character. And so you can see very quickly we end up with 1 byte for the actual character and 100 bytes or more for the overhead, for the metadata that the CRDT needs to maintain. And this is really bad news because, it's a really bad ratio of data to metadata. So I want to talk briefly about some experiments we've been doing as part of the AutoMerge project, which is a CRDT implementation that I work on. And I've put a lot of effort over the last few months into reducing the metadata overhead of this. And so I'll start with the results here, which are summarized on this table. So there's a lot of data here, but let me talk you through this bit by bit. So the data set that we're looking at here is the editing history of an academic paper. So we wrote a research paper using a homegrown text editor and recorded every single keystroke that went into the creation of this paper. So the end result is a LaTeX file described in content of this paper of about 100 kilobytes is just the plain text of the LaTeX file. And about 300,000 changes went into the creation of this document. So a lot of characters were inserted, and then some of them were deleted again. And we also recorded every single time the cursor was moved. So each character insertion or character deletion or cursor movement counts as a change, and we have about 300,000 changes like this. And we wanted to keep that whole change history so that we could see, for example, how the document evolved over time. So just like with version control, you want to see past versions of the document. And the simplest way of doing that is just to keep a log of all of the CRDT operations that have been performed. And if you do this, keep that log and encode this log in a basic JSON data format, it takes about 150 megabytes. It gzips very nicely down to about 6 megabytes, but it's a huge file compared to the 100 kilobytes of just plain text without any of the CRDT metadata. But what we've been able to do is to actually compress this down and still maintaining the full document history, so without actually throwing away any of the change history. Just by encoding the data in a more clever way, we've been able to get this down to about 700 kilobytes. So this is a factor of 200 difference compared to the 150 megabytes that it was taking previously. And as I said, that still preserves the full change history. We can then compress it further by allowing certain parts of the history to be discarded. So for example, if we say that we're not going to record all of the cursor movements, we only want the editing history for the text, but we don't want the cursor movements, that saves another 22% or so. If we want to just throw away the editing history for the whole text as well, and keep only the CRDT metadata that is necessary for merging the current version of the document, then we're down to about 228 kilobytes. So this is now only about twice the size of the raw text without any CRDT metadata. If we gzip it down, then we're actually almost at parity at almost 100 kilobytes. We can further compress it by removing tombstones, that is forgetting about characters that were deleted. Now, this brings us down the overhead down to only 50 kilobytes. So only 50 kilobytes for maintaining the unique IDs for each character. But at this point now, we can't necessarily merge across users who've made edits concurrently with the removal of the tombstones. So we can get down to pretty small file size here, even without discarding any tombstones and even without discarding any editing history. We can still make the whole thing quite compact. And I will show you very briefly how we do that. So Firstly, we continue storing the full set of all of the operations that have happened. We give each operation a unique ID, which is just a Lamport timestamp. Lamport timestamp is just a pair of a counter and an ID of the node or the actor that generated it. And like in RGA, our algorithm references the ID of the predecessor character in order to identify where a particular character goes in the document, where a particular insertion goes. And then we just store all of the operations in the order in which they appear in the text. And if we do that, we end up with a table that looks something like this. So in the first two columns, we have the Lamport timestamp for each operation, and each row in this table here is an insertion operation. And you can see in the second, as in the third and fourth column, we have the ID of the predecessor character. So here, the second character is inserted after the first, the third character is inserted after the second, and so on. We then have the actual UTF-8 string, which is the text that is inserted with every single character insertion, which is HELLLO. So we have hello with 3 L's. And in the length column, we have the number of bytes in the UTF-8 representation of this character, which is just 1 for each of these, assuming English text. And finally, we have the last two columns, which record if a character has been deleted. And now we can compress this data using some very simple tricks. So what we're going to do is we're going to encode each column of this table separately. And so we'll start with the first column. The first column contains the numbers 1, 2, 3, 4, 5, 6. We can compress this really well by first delta encoding it. That means we take the difference between each number and its predecessor, and just by calculating those differences, we turn 1, 2, 3, 4, 5, 6 into 1, 1, 1, 1, 1, 1. We can then run length encode this by saying we just have 6 repetitions of the number 1, and then we can use a variable length encoding for integers to encode this in just 2 bytes. And this variable length encoding here, what this does is it encodes small numbers in 1 byte and then slightly larger numbers in 2 bytes and bigger numbers in 3 bytes and so on. So here we've encoded the first column in just 2 bytes, which is 1/3 of a byte per operation. The second column, well, very similar process. What we do is we make a lookup table from actor IDs to small numbers. Then we have 0, 0, 0, 0, 0, 0. We run length encode it again. We again use the variable length encoding of integers. And again, we have encoded that column in 2 bytes. Let's look at the text column here, the UTF-8. Well, note that we've recorded the length of each character in bytes separately. So we can look at the length column, which is just 1, 1, 1, 1, 1, 1. That again, run length encodes really simply. Now, the character column, this UTF-8 column, we can just concatenate the bytes from each of these. And so now we've just got hello with 3 L's, which is just encoded in 6 bytes as a UTF-8 string. And then separately, we record for the deletion column, we record the fact that the third L was deleted, and so that our final state of the document is hello. So then we just need a little bit of extra metadata, which tells us like when did each change happen and what is the range of operation IDs, the counter values for each change. And then this allows us to reconstruct what the state of the document was at any past point in time. And at the same time, we've stored the full document history without discarding any history, and we've done so in a way that is very efficient and uses only a small amount of storage space. So that brings me to the end. As I said at the beginning, CRDTs are tricky. They are difficult to implement well and easy to implement badly. And we've seen 4 problems that have been part of the problem set with CRDTs for quite a while. That is interleaving problems. How do we perform moves on lists and on trees? And how do we represent them efficiently so that they don't use too much storage space and too much network bandwidth? So as background, if you want reading, here is a list of papers describing a bunch of text editing CRDTs. And here are the things that we have written, providing more details, giving all of the details on the algorithms of the things that I've talked about today in this talk. All of the slides are online, so you'll have plenty of time to find all of these papers online if you're interested. So that brings me to the end. Thank you very much for listening, and I think we still have about a quarter of an hour for questions.
Thank you, Martin, for the great talk. We have 10 minutes for the questions left. And the first question from Dmitry. He's asking about the delta CRDTs that were introduced in 2016, I guess. And the question is, what do you think about it? How it interleave with your research and work? Can it help? And what do you think of the future of it?
Yes, delta CRDTs are interesting. So the CRDTs I've talked about today have all been operation-based CRDTs, as you probably notice. And the difference between operation-based and delta CRDTs is a little bit subtle. But the key idea is that with delta CRDTs, you can essentially take several adjacent operations and compress them down into a single delta. And so you can communicate this about as efficiently, or even more efficiently than an operation-based CRDT. But at the same time, you have the nice properties of state-based CRDTs, that the merge function is idempotent and so on. The trouble with delta CRDTs is that all of the text editing and list CRDTs are actually operation-based. And so you probably could construct a delta-based CRDT for text editing, but it doesn't really make very much sense, because this idea of collapsing several adjacent operations together, that makes a lot of sense if those operations are counter increments, because you can take several increments to the counter and just replace them with a single increment for a bigger number. But if your operations are insertions and deletions into text, then this sort of condensation doesn't really make as much sense anymore. And so for that reason, the types of CRDTs that we've been looking at, where we want text editing and we want lists, for those delta CRDTs don't provide very much benefit. And so we've been focusing on the operation-based. But if the CRDTs you have are mostly counters and maybe sets, for which they are good delta-based CRDTs, and registers, of course, for those types of CRDTs, delta CRDTs make a lot of sense.
Okay. The second question, which is continuation of the first one, is whether it is possible to introduce some kind of snapshotting or based snapshotting for the operation logs of the CRDTs. Yeah. What do you think about it?
So I'm not sure, it's this question about the move operation, where we have the log that we have to undo and redo, presumably. So in the context of this move operation, you need to maintain the log of operations to undo and redo, at least until you are certain that up to a certain point, there will be no more operations with a timestamp that is less than that point. So this is also known as causal stability. And so that is, we have a certain frontier where we know that all of our nodes are caught up at least to a certain timestamp, and all future timestamps will be greater than this particular value. And then once you know that, then you can throw away the log for any timestamp that are less than this causal stability threshold. And so in that case, yes, you kind of have a snapshot. In fact, it's a bit better than a snapshot, because you just throw away the log, and because you don't need it anymore, because you know that you will never have to undo any of those operations again. So you effectively get this kind of snapshotting behavior. But you do need to maintain the log up to the point of causal stability. And this can be a problem in practice, because if you have just one node that is offline for a long period of time and then comes back, that one node will hold up the progress of the causal stability. So because the other nodes don't know if that offline node has got any changes with a lower timestamp that it hasn't sent yet. And so that is a problem with all of these causal stability problems, that just a single offline node holds up any garbage collection process. So that is finding good solutions to that, is that that are less robust, that are more robust to nodes being offline. That is still an open question.
Okay. I'm pretty much curious about, for example, if we have an architecture in which we still have a single server which does the synchronization, or let it be sequencing, it still does make sense to use the CRDTs in place of the OTs. And
So
maybe you can elaborate a bit about the disadvantages and advantages of those algorithms in the presence of
yes, indeed.
a single point of scenario.
Yes, so until recently, until this work that I just described, where we've been improving the efficiency, metadata efficiency of CRDTs, I would have said that generally OT, operational transformation algorithms, are more efficient. And so if you're willing to assume this single central server, then you can probably get better performance, better memory use, better network bandwidth use using OT. Now, as you can see from our experimental results, by compressing the CRDT metadata, I think actually we are able to get CRDTs to a point where, in terms of their performance and their memory use and network bandwidth use, they are actually competitive with OT. So in that case, that distinction then is no longer relevant. We still need to do more experiments to really verify that comparison, that performance comparison to OT. But that is where we're heading. In terms of other differences, it depends again a bit on the types of data structures you want to support. So OT algorithms are pretty well established for text editing, where what you've got is just insertion and deletion of individual characters in a linear sequence. Things get a lot more difficult if you want to support richer data types. So if you want to have trees, for example, yes, there are OT algorithms for trees, but they are much less well established, and you have to there's much less existing literature and implementations of them. Even more so if you want to have things like move operations for trees, like we've talked about earlier. And designing those kind of OT algorithms yourself can get very hairy. So as we've seen, there have been a lot of broken OT algorithms in the past where people have designed transformation functions that they thought were correct and then a few years later turned out to actually be wrong, and in certain circumstances lead to inconsistent results. So I think my recommendation there would be that if you're only doing plain text, no trees, no rich text, and you can use an off-the-shelf OT implementation, then you'll probably be fine with OT. But if what you want to do is support richer data structures, then probably you want to be using an off-the-shelf implementation of either CRDTs or OT, because both of them are somewhat fiddly to implement. And I think, as I said, CRDTs are getting performance-wise competitive with OT, which then means that the comparison really just comes down to, are you willing to make this single server assumption? So I should note there that, even if you are performing your communication through servers, it can still be valuable to have the CRDT approach, because it allows you to have multiple replicas of the servers, and those replicas don't have to be coordinated in such a tight way. So if you want to allow having replicas in multiple data centers for fault tolerance, for example, then using CRDTs gives you a very natural way of extending the replication, that not just the end user clients are replicas, but also your data center side servers, you have multiple replicas. And that sort of synchronization then becomes really easy with CRDTs. Whereas with OT, from what I've heard from Google, they have had to put a lot of effort into making sure that there really is always this single server. So, if you've got a Google Doc open and you're working on it, there's literally a single container running somewhere in one particular Google data center, and that has got the primary copy of that particular document on it. And if that particular server goes down, then Google has a complicated failover protocol to make sure that is failover to having a different server that acts now as your single server, while at the same time preserving the properties that are required in order to make OT work correctly. So I think making OT work reliably on the server side is tricky, because you have this need for maintaining that single server, even in the case of server failures. So yes, long answer, but hopefully that gives you a bit of a sense of the trade-offs in this space.
Okay, thanks. We have 1.5 minutes left, and the last question here will be, what, for example, if we want to implement the Vim style editing with the CRDTs, and for example, you showed the two cases when we have the move operation, the move for a single character and the move range, which looks like pretty much like primitive operations, but we don't have a universal construction schema for that. And the question is it possible to construct universal operations, for example, from what we have already in a theory plan? And for example, can we build a Vim-like editor with the CRDTs, or how to merge?
So with Vim-like, you mean that it's you have this modal interface and you have operations that act, for example, on cut an entire sentence and paste that sentence somewhere else. I assume you mean something like that.
Like group
I think
operations or something.
Yes. So that should be possible. I mean, essentially you can condense most thing down into just copying or cutting character ranges, inserting them and deleting them. There's an interesting question around, for example, can you take a cut and paste where the cut happens first, but then the paste happens at some later point in time, and change the paste such that it actually becomes a move of the original cut operation. There's no existing implementation that I've seen which does that, but I think it should be possible in principle. But in terms of universality of these things, like the challenge there is always, can we make it such that that the CRDT's behavior in practice is what the human users expect? I think that will have to be the criterion on which these things get judged, and that can really only be determined by use in practice and seeing if it behaves like people expect it to behave.
Thank you very much, folks. Thank you, Ivan, for being the man in the middle between the audience and Martin, and thank you very much, Martin, for your talk. I remind you that it was talk CRDT, the hard parts, by Martin Kleppmann, and we are waiting for all of you in Zoom. So for joining our Zoom discussion zone, please, the Zoom button just under the player, and join the discussion zone. And thank you very much for the broadcast, Ivan and Martin. It was very interesting. So thanks a lot. And it's
great in the discussion zone.
And this is a great honor for all of us to have you both on board this year. Thank you very much, guys.
No problem. Thanks all for tuning in.
Yeah.